All right, so with that said, I'm going to talk about a few things. Wow, I don't know if I can get slightly less of a suntan from the, from the light there. Okay, so what I'm planning to talk about, first off, just very briefly, is the nature of information. Because everything else that I'm going to put in this talk needs us to think about what we mean by information. And there are many things you might mean, but we're going to be thinking about it in a way that leads us to the idea of the quantum bit, which I expect most of you have heard of in some way or another, and it has a contracted name, qubit. And then we get down to business and we think, what might you use your quantum bit for? And I will say a tiny bit about quantum sensors, a medium-sized bit about quantum communications, and then a lot about quantum computers, because that's my personal interest. All right, so I said we needed to sort out what we mean by information for the purposes of this talk. And what I mean by information is really ones and zeros. So everything that we can process with today's computers is ultimately something that can be described with numbers. And if it can be described with numbers, then it can be described in binary, which is ones and zeros. And that is the secret of the current information age we live in. The secret is that ones and zeros are pretty easy to store in a wide variety of ways and even to process. It's about as easy as it could be. You just have to build a gadget that can be one thing or the other, and you call one of them 1 and one of them 0, and is stable in that respect. So here's a few different technologies. I sometimes ask for a show of hands for anyone who can remember the era of punch tape, but I think it's, someone's bravely putting their finger out, right. My dad used to work with computers in the relatively early days, and I found some punch tape around the house and had no idea what it was. But you can see that it's a lovely way to store zeros and ones. That's what it is. You knock a hole through it if, say, you want it to be a 0, and don't knock a hole through it if you want that to be a 1. And then that's going to just stay like that for years. And if you shine a light for it, for example, you'll be able to turn that into an electrical signal. Zeros and ones, nice and stable. In the top right, you can see a circuit, which you might then put into an integrated chip. But maybe this is a bit more contemporary. Here we have a little diagram to explain to us how hard drives, which we all used to have in our laptops and still have in larger computers, magnetic hard drives work, have lots of little magnetic particles. And you just divide the area up into regions, and you say each region is storing 1 bit. And if most of the particles point left, you say it's a 0, or actually the other way around in this diagram. And if most of them point the other way, you say it's a 1. Now, over time, some of these guys might get knocked to point the wrong way. But that's okay. As long as most of them are pointing left, or most of them are pointing right, you'll still be able to see, is it supposed to be a 0 or a 1? And you can even come along and read, this is supposed to be a 0, but it's getting a bit weak, and then whack it back to full force by applying a magnetic field to it, and now it's a nice strong 1 or 0 again. So these are very stable ways to store and ultimately process information, zeros and ones. It's not hard to conceive of technologies. You can even conceive of some pretty crazy ones involving things like ball bearings and stuff that will store zeros and ones for you in a robust way. Now, there is a long history of physicists being interested in what seemed to be the technology of the day, and then thinking about, okay, this is fascinating stuff, but what's the basic laws of the universe that are governing it? And I suppose the most obvious example would be thermodynamics. And so in the age of steam engines, people wondered about, okay, this is amazing, we're turning steam, heat basically, from burning things into mechanical action, but what are the basic laws of physics that govern that? That leads us then to the entire theory of thermodynamics, which then shows us brand new insights, like, for example, how efficient could a solar cell possibly be? You can answer questions that don't seem to have much to do with steam engines because you were inspired to look into that area. And computing is no different. People have been fascinated to ask, what's the basic physics of computing? They're amazing and they're great, but what can we say about what the laws of physics will or won't permit for computing? So one person who was very interested in this question is a guy who lives in Oxford. It's a really interesting guy. I should suggest you have a look because he has many lectures and things online, David Deutsch. And David became interested in this question, and it can be rephrased, I think, effectively to say, what is the basic physics of the bit? What would the universe have to... What's the limits in our universe about storing something that has to be one thing or the other? how far could we push it? It's clearly a technologically interesting question, as well as just a very nice philosophical question. So we might say, all right, let's imagine using an atom, a single atom, to store a bit of information. Could we do that? Let's have a think through. So there seems like it's pretty promising. This is a different sort of artist's impression of an atom. You'll see this later on if I can make my animations work. But atoms have a condition which we would call the ground state, which means the atom's there, it exists, but it's got no extra energy. It's like an empty battery. It's got nothing extra to give you. And so we could say that's a zero. If our atom has no extra energy and is in its ground state, we'll say that's a zero. And then we could focus on putting a unit of energy into it, and we could say, all right, that when it's charged up, our atom is a 1. Well, that would be okay. We could think about doing that. For a practical technology, we would have to worry about how long it lasts before it maybe loses its energy and things like that. But at least this would be quite possible in principle. And then to really understand what would happen if we tried this, we need to use the laws of quantum physics, which is what governs, well, really the entire universe, but certainly governs the way things like atoms behave. All right, so what happens when we do that? So then we have to go to something called the Schrödinger equation. There aren't many equations in this talk, except actually towards the end, where I just give a hint about some of the work that my group's doing in Oxford. But on the whole, it's very sort of equation-free. But here's one. This is the E equals mc squared of the quantum world, Schrödinger's equation. It's an equation which any mathematical description of a system must obey if it's going to be legit, if it's going to be a condition that could exist in our universe. And fortunately, we can indeed get a mathematical description of an atom in its ground state that satisfies the Schrödinger equation. And what that's saying is, yeah, that state of the atom is a possible thing that can happen. So yeah, we can have our zero. And we can alter our mathematical description, and now it's giving us a description of an atom with energy inside it, an excited state of the atom. So these are both solutions to the equation. That actually, if you want to know where it goes, and I can't quite reach it, if I just stand underneath, it's inside that vertical line and that what looks like a greater than symbol, okay, that ket as we call it. We have a little symbol there. That actually means the state of the system, which is a piece of mathematics. But crucially, that would be one solution, one thing that makes the equation happy, and that would be another. But here's the problem, or here's where it gets weird. It gets weird because the Schrödinger equation is almost too simple. I know it doesn't look very simple, but it's too simple because it's a linear equation. And that means if you have one way to solve the equation, you say, oh, my atom is in the ground state, that's legit, that solves it, and another possibility, the excited state, you can actually also have them both at once. So we can say, oh, yeah, also, my atom is both in the ground state and the excited state, and put that into the equation, and the equation's equally happy with that. But what does that mean? Up until now, we were pretty happy saying, sure, it's a mathematical description, atoms exist, that's fine, that's fine. But now it's saying an atom can be in two different conditions at once, what we would call a superposition. And that should worry us. It worried the heck out of all the great thinkers that gave us this theory, including Einstein and Schrödinger, because it seems to be now counterintuitive. All right, so what we might say, what's this trying to tell us about the universe? What does it mean to say that something can be two different things at once? So this led to the famous, I won't talk about it now, but I just have a picture here to remind us. This led us to the famous Schrödinger's cat, which was a thought experiment, where we imagine a quantum level event like something to do with an atom, for example, a radioactive decay of an atom that might or might not happen, could be in two conditions according to quantum physics, and we just scale it up through a piece of apparatus that's inside the box into something that will or won't kill a cat. No one has ever attempted this, fortunately. It's both unethical and impossible in practice in the lab, so don't worry. But there's nothing in physics to say that this wouldn't indeed happen. And that as long as this stays sealed off from the rest of the universe, which is why it's inside a box here, it has to be a perfect box. As long as it stays sealed off, then inside that box, we can actually have such a crazy thing as a cat that is both dead and alive at the same time. That's, an unsatisfactory thing philosophically for many people, and huge amounts of work have been done to try and find a different way of looking at things. For our purposes, we don't need to find a different way of looking at things, we'll be fine with it. So rather than giving the rest of my talk about philosophy and saying, well, what could it all mean? Does it mean there are parallel universes that are sort of coming apart as decisions are made? It's all very fascinating to talk about. But instead, we're going to think, is it useful? If the universe really is that weird, and things can be in two states at once, does that lead us to anything? Does it allow us to go beyond today's computers? Today's computers, as we were discussing, are all about making a 0 or a 1 be definitely one thing or the other. If we now say, oh yeah, also you can be both at once, does that mean we can do new things that weren't previously possible? So the answer seems to be yes, which is why it's so exciting. If it was like no, at the end of the lecture, right? It's like, and no, actually you can't. Okay, so we can do, or at least we believe some things we haven't been able to try yet, other things we have proven do work. So now on to the ways we might use our qubits, our quantum bits, these interesting gadgets, and don't worry, I will come back to the atom example and some other examples of what they really are, but for now, it's just a quantum thing, like Schrödinger's cat, that can be in one of two different states. How will that lead us to better or more interesting ideas for sensors, or communications, or what might be the ultimate computer? So, I have to introduce you to a problem that's going to be a recurring theme through this talk, which is that qubits are fragile. And that's really part of the reason that we don't see things in superposition, two places at once, in the everyday world. The formal word for it is something called decoherence, which means the universe does actually make up its mind. Whether am I over here or am I over here? Is the cat dead or alive? That will happen to any quantum system, and it will wreck our qubit, basically. Now, in summary, qubits are fragile things that can easily be forced to, we would say, collapse into one state or the other. What can we do about that? Or is it even a problem? So, when we come in a moment to think about computers, we will see that is a problem. Because the inside of our computer is going to be made out of qubits, and we don't want them to just collapse and become one thing or the other. It's all about maintaining this magical superposition. It's also not great for communication. It's not certainly going to help us if the particles, which will be photons that we use to communicate, sometimes collapse. But for sensors, it's good. It's good because a sensor is precisely some kind of gadget that is very sensitive to its environment. And so if we can actually turn a bug into a feature, so to speak, we can get our qubit and say, what's this? The qubit is disrupted by everything around it. Great. Then now it's going to be a highly sensitive sensor. Now, that is, in my mind, but then I'm biased because I work at the other end of the spectrum, very interesting, but the least interesting thing. It's more interesting to think, what happens if we can keep this superposition thing going? But I will show you quickly an example of an idea for a quantum sensor which does work, and as far as I know is not in sort of devices that you'll encounter in hospitals or whatever, but it is already a demonstrable technology. So here's a question for you, which seems like a bit of a random one. What gives pink diamonds their colour? Well, impurities in the diamond. A perfect pure diamond is just transparent. The pink very often comes from a particular kind of impurity. So this is appropriate that we're in a chemistry lab, and I didn't realise that I actually have got a ball and stick diagram in my slides, but that's very suitable. I should have asked for one to be put on the desk here for me, really. Now, there's a kind of defect that happens inside diamond that's actually really interesting. What happens is you sometimes get a nitrogen atom in there, pretending to be a carbon atom, and sitting where there ought to be a carbon atom. But that isn't very interesting on its own. Another problem that can happen in diamond is you can have a missing carbon atom. It's called a vacancy, where you should have a carbon atom according to the repeated pattern. There's just nothing. And that is another not very interesting problem that diamond can have, or defect. But sometimes these two things are next to each other. A nitrogen atom is substituting for a carbon, and next to it there's a nothing, there's a void, a vacancy. And this is called an NV center for obvious reasons. It's a nitrogen vacancy defect center. It just so happens that that thing is one of nature's qubits that we might choose to harness in our technologies. What happened? I won't go through it because it's really rather complicated, but it traps, can become charged. So this little defect inside diamond can have an electron trap there. The state of the entire little complex there is just like that atom we were thinking of earlier. we can either imagine that it's in its ground state or that it has, extra energy. That's our qubit, our 0 and our 1. And the great thing about the NV center is, and we'll see this again with some suitable atoms later on, light, we can tell, when we want to know, are you a 0 or a 1, which we eventually will always want to find out for any technology, because we need to read out the answer. We can do this with light. So we can contrive that our NV center will scatter light, let's say, if it's in state 1, but not if it's in state 0. So we can actually look at it with our technology, in principle even with the human eye, and tell, was it in state 0 or was it in state 1? But until we do that, it can be in this strange superposition state. And the way that people suggest making this into a sensor is the following, roughly. You take a piece of diamond, not in the shape of a diamond ring type of diamond, but as essentially a little cone like this, and you contrive that there is an NV center, so you might find a piece of diamond that naturally has a nice NV center in it, and then etch the diamond away, or you might implant an NV center, which I could go into your tip of this piece of diamond. And now, what you do is, you can read and indeed set the state of your NV center, your little qubit, in there, in that piece of diamond, with a laser beam, and then you can put it into your no extra energy, yes there is extra energy, your 0 and 1 superposition. This is very sensitive to the environment. Once it's both things at once, like Schrödinger's cat, it's very sensitive to, for example, magnetic fields. And you can use this then to probe nature, to probe the magnetic fields from, say, individual molecules with extreme precision, because it's just a tiny single point, but it's so sensitive to magnetic fields because it alters the qubit, that if you put the qubit in a particular state, expose it to a magnetic field, and then come later and check what state it's in, what you find depends on the field that it's experienced. So I can go into that in a little bit more detail if people want to ask me, but the basic message is, here's a qubit, we don't protect it from its environment. To a physicist, the word environment doesn't mean the same as to an environmental scientist, like the health of the oceans and so on. The environment is just everything around the actual little device that you're interested in. So here, the NV center sitting inside its little piece of diamond is the device, and the environment is everything, including this molecule, this piece of DNA, essentially, that we imagine ourselves scanning with our super-sensitive detector based on a qubit.
Excuse me.
Yeah?
So you talked about decoherence, but
yes.
How does that differ from observation and collapse?
Yeah, I mean, it doesn't really differ. It's simply that we're exploiting the fact that we understand decoherence so well. So let me say a little bit, just a word more before I go on about how we'll actually do this. So we start off with our NV center, let's say definitely with no extra energy. And then we put it into superposition of 0 and 1 at the same time. And we do that in a way that, I won't go into it, but we can reverse the same process. So we could turn it from 0 and 1 at the same time back into 0. And we can go either way we want. That's under our control. So you take your qubit, it's initially in state 0, you turn it into 0 plus 1. You create that state. And if nothing happened to your qubit for, let's say, 100 nanoseconds, depends on how strong its environment is, but let's say that as an amount of time, then when you come to reverse the process and turn it back from 0 plus 1 into just 0, it will do that because nothing has changed. And then if you read out its state, you'll see a 0 for sure. On the other hand, if the qubit is exposed to a field, what will happen is you start from your state 0, you turn it into 0 and 1, this strange superposition state, and then because it experiences the field, that changes the nature of the superposition. So I wasn't going to get into this, but I'll just mention the word phase. So it's not just that it can be 0 and 1. There's a relationship between the 0 and 1 parts, which for those of you who know about complex numbers, which I guess is a lot of you, is just a complex number. So there's a phase there, like an angle, really, between the 0 and the 1. Now if you create it with that angle as 0, when you later come to reverse the process, you'll be able to reverse it, fine. But if the environment has caused that phase to change, and a magnetic field will do this, then when you come to try and reverse and go back from 0 plus 1 to 0, it won't go back. It will go to a different state because it's changed in the meantime. And the reverse of what you did to make it no longer will, so to speak, unmake it. And now when you measure to say, oh, okay, are you in state 0 or state 1, you won't necessarily see 0. You might or you might not. And so that difference tells you that you've been in a magnetic field strong enough to change the state of the system. Now, if you now take away the idea that this is a sensor and just imagine that this is a component of a computer and we're trying to do a long, fancy calculation, and these fields are not something interesting from some molecule like DNA we're trying to scan, they're just stray magnetic fields that exist in the lab, then the same kind of thing will happen, but now you just don't want it to happen because it's made all your qubits become a bit random, which is effectively the same as, it makes them identical to qubits that had collapsed, but you don't know which state it is. So, long story short, it's the same physical phenomenon. It's a question of whether you harness it to make it into a merit, or you try and fight it, which we will come on to in a moment. All right, good. So that's the end. I won't talk about that. It's just another version of this. So that's all I have to say about sensors, although I'm quite happy to try and say a bit more if people ask me, but I should say it's not my specialized subject. And we're just getting gradually closer to my actual area of expertise, I guess. So how about communication? Let's move away from just saying qubits are very sensitive, that's good for sensors, and say, all right, what kind of fun stuff can you do with quantum phenomena that you wouldn't be able to do if you didn't have qubits, if you just had classical bits? So I'm going to talk about a communication scenario which is all about security. So imagine you're a spy. This is not what real spies look like, I'm reliably informed, disappointingly. So not that kind of spy. A more realistic kind of spy would be someone who needs to send a message, and they need to make sure that that message, if it's intercepted, cannot be understood by the enemy. So what we could imagine is we could say we have Alice, which way around have I got it? Alice is at spy headquarters, but Bob is the spy who's on a mission. And Alice, that's the wrong way around, I apologize. If Bob's on the mission, presumably he has the message. So then Bob has vital message. In fact, let's see which way the slides, let's see which way they decide to come down. Yeah, all right. So Bob is receiving it. All right, so let's just imagine these labels are the other way around. Alice is the spy. Fine. Alice has a message that she wishes to send, and she wants to send it with total security. That means if someone intercepts this message, they just can't make any sense of it, however powerful their code breakers are. Is this possible? It's actually already possible with conventional physics to do this. And this little picture here, which I think I got from Wikipedia, is a genuine, I believe, example of the kind of thing that you need, which is a code book. Alice and Bob must share a record of essentially some random numbers. And you can imagine you literally have this tiny, weeny little book in which, I don't know if you guys can see, but I can see, it's just like 1, 8, 4, 9, 9. It's just a random sequence of numbers. Alice and Bob have both got this, and it's an identical copy. But no one else has got that particular pair of books that are matched to each other. Now, Alice wants to send this message, PM kidnap plot. I don't know who wants to kidnap the PM, but then we leave that to our imaginations. But that's what the message she wants to send. How is she going to do it? Using this book that she's got. What she does is she uses any scheme you like for turning letters into numbers, such as the ASCII scheme, which is the one that many of our computers use. So let's say the letter P is number 16. I guess actually that's not ASCII, that's just the alphabet that I've chosen there. But it doesn't really matter. You just have a standard way to assign numbers to letters, and that's not secure at all. I mean, anyone could just, after seeing several of your messages, would just guess your numbering scheme. That would be pathetic. But what you do is you take a couple of digits from your code book, such as 95, and you add it on. If it comes to over 100, you'll only need the last two digits, and that, so it would be 11 in this case. And you will now just send that, if you're Alice, you can send that any way you like. You can send it over the radio, you can shout it from, well, that would give you away as a spy, I suppose, to shout it from the rooftops. But you don't need to worry about the enemy getting that pair of digits. Because the enemy does not have the number 95 in order to make sense of it, but Bob does. So when Bob reads that 11, and he must be at the same point in his code book as Alice is, he will go and say, I see that Alice is on 95. She's added on 95. I'll subtract it. Because he only sent two digits, he'll actually get minus 84. But that doesn't panic. He says, that's okay. That must mean that Alice went over 100 and just sent me the last two digits of the number. So I'll add on 100. He figures that out. And he gets back the letter P. And of course, it goes on like this. Alice then takes the next two digits and adds it to the number that corresponds to m, and so on. So she sends a sequence of numbers. Now this scheme is invincible. It doesn't matter how powerful the enemy is. If they just have the series of numbers like 1, 1 and each sequence of numbers, they cannot make any sense of it without the codebook. So isn't that just like the solution? Why don't we use that for our security? Why is it that there's any risk at all that hackers can intercept and understand our information? What's the problem with this as a communication method? Would anyone like to suggest to me what the problem with this? It's used, by the way. You can actually get a company, if you trust that company, you need to trust it, will actually provide you with a gadget which fills up a hard drive with randomness. And it will actually fill up 2 hard drives. So any kind of drive you like, I guess, USB stick if you want, but it will fill up that data storage device with random zeros and ones and a matched partner to it. And then you just have one each, and now you can communicate with your friends who's gone off to America or whatever, using that information that's been stored in the modern equivalent of the codebook. But what's the problem with it? Why don't we just do that all the time?
So the books could be stolen as they're being transported.
They could be stolen as they're being transported. That's quite true. But there's a more fundamental problem, and that certainly is a weakness. But there's a more fundamental problem than just making sure no one ever gets a look at your copy of the book, so to speak. Yeah?
You have to generate the numbers somehow.
There it is. So what I didn't stress, but you pointed out to me, so let me say it again more clearly now, that you're not allowed to reuse these numbers. After Alice has used 95, she must cross that off and then use the next pair of numbers and then the next. It's crucial that there's no pattern in the numbers and that each time we encode a letter, it's completely random. And if we kept reusing the book, it wouldn't be random. A very clever opponent who got a copy of all our messages would be able to start to guess things because we were reusing the book. So the book will run out, and so will a USB drive full of zeros and ones, so will a big fat hard drive with terabytes of randomness. After you've exchanged that much information, might be videos, all sorts of things, you've got no more capability to securely communicate with the other person. You'll need to meet up and exchange a new copy of the codebook. And that's what stops this being a very practical method, right? I don't want to have to meet up with everyone that I might want to communicate with and share a secret, set of information with them. I could do that, but I don't want to. It would not be a practical communications solution, except in extreme cases, like indeed a situation with a spy. So it would be.
The same is true for any other encryption scheme where you have to exchange a key. The important part, you have to have a key exchange mechanism.
That's right. So I will come. You're quite right. You're quite right. So if we had a mechanism to get the process started, okay, let's phrase it that way. You're quite right. The problem is this resource runs out. If we had...
Can pi be your codebook?
Pi, the number pi,
yeah.
It goes on forever, but it's pretty guessable, right? So, your secret would have to be, I'm going to use pi, right? And that's fine, but then all the enemy has to think is, I wonder if you used pi or e, and then they've got your code. So the point about this is because it's random, there's no structure to it. There's no way that anyone can guess it, not even with the quantum computers will come on. It's invincible as long as you don't reuse your random zeros and ones, as long as they're perfectly correlated and you don't reuse them, and you don't run out, but you will run out. Can quantum help with that side of the problem? So, yes, it would be boring if I'd set all that up and there's no help, but it can help. So the point of this slide is just to say it's not just spies. This kind of thing can be interesting to anyone who wants to be able to securely send information. You might want to securely talk with your doctor or with your bank. So it doesn't have to be a sort of villain in the story at all. Now, there's various ways that quantum can help with this problem, but the most elegant by far, in my opinion, is a scheme due to a guy called Arthur Eckert, who has been at both Oxford and Cambridge, so I'm not having to pick a favourite there. And Arthur came up with a scheme based on a thing we haven't talked about yet today, which is quantum entanglement. Quantum entanglement is really just superposition again, but now when two systems are involved. So if I have 2 qubits, they could both be 0, let's say I had two bits, they could both be 0, or 0, 1, or 1, 0, or 1, 1. 4 possibilities. If I take just two of those possibilities, such as they're both 0 and they're both 1, also fine. And quantum physics, we already know, will allow us to combine solutions, and that's still a legitimate condition for the universe. So we can have both state 0, 0 and state 1, 1 existing at the same time in superposition. But now we should understand that the left-hand qubit is in Alice's possession, and the right-hand qubit is in Bob's possession. Now, when either Alice or Bob measure their qubit to see is it 0 or 1, it will collapse the state of this entangled system to one option or the other. So that means that Alice and Bob will always either both measure 0 or both measure 1. But until they measure, they don't know what they're going to get, and neither does anyone else. Now, this is another massive tangent leading to huge amounts of philosophical literature, because, and we're not going to get into this, but people worry about whether or not this kind of thing existing is consistent with the universe being what we call local. Is it possible for these things to neither be 0 nor 1, but as soon as one of them is measured, then they both are? That seems to require instant communication or something, and that is another philosophically worrying point. But we won't go into that at the moment, because we are in the mood to talk about practical technologies. So, this weird entangled state, how can I use it? All right, so this is things I've just remarked on. We're going to get random 0s or 1s. Alice and Bob will both get the same, that's great. And that sounds fine. And then there's an extra property, which is what makes this so different to a scheme that could just be, I'll send you both we'll both have a 0 or both have a 1. Monogamy of entanglement, this statement. If your qubit, Alice's qubit, is entangled with Bob's in this way, then it cannot be entangled with anything else in the universe. It's a lovely sort of playful phrase, monogamy of entanglement, right? So qubits can't cheat on each other. If two qubits are entangled, that's it. They cannot, physics will not permit them to be, I should strictly say, maximally entangled with anything else. And that has profound consequences when we think of how we might use this as a technology. So now let's imagine we have this. We have Alice and Bob, and they want to be able to communicate with each other, just like we've described before. They may indeed share a bit of random information, as this chap, sorry, I obviously don't know your name, was suggesting, that allows them to recognize one another as legit. But they don't want that to ever run out. They want to be able to keep on talking to each other, and as if they had a magically replenishing codebook that didn't need them to meet. So what they do is they contrive that there's a source of entangled particles, and Alice receives one of each pair, and Bob receives the other. Now, how does this help them? Well, Alice, when she receives hers, will measure hers. Bob will measure his. And they will always see, well, okay, so there are some subtleties that I'm skipping over here to do with them measuring in different bases. And these are actually the hard parts of the scheme, because otherwise any one of us could have thought of this and wouldn't take Arthur Eckert to work it out. But the bottom line is that they will end up with a perfectly correlated sets of 0s and 1s, and no one can have taken a copy of that. Otherwise, you see, if this was just a regular communication system, sure, we could send out 0s and 1s down a wire in the normal way, but an eavesdropper could just watch and just take a copy of everything as it came along. And then the eavesdropper would have a third codebook, which would make the whole scheme pointless. But monogamy of entanglement means anyone messing around with these qubits as they go from the source to Alice and Bob will necessarily mess up the entanglement, and that will be something that Alice and Bob can detect is happening. So we usually in these stories have a third character called Eve, the eavesdropper. And one can show that Eve cannot monitor the communications, cannot monitor the creation of the 0s and 1s without messing it up in a way that Alice and Bob can detect. And then they'll say, someone is messing with the line. I can no longer trust this to produce my random 0s and 1s. So it's possible to break the scheme so that Alice can't communicate with Bob because her code generator is stopped working. But then denial of service is always a possibility. The thing is that Eve can't do this stealthily so that they keep on talking to each other, but now she's able to get the message. It doesn't help her to be higher tech than they are. So even if Eve is super high tech and has a big computer behind her, she still can't do anything because it's physics itself, as long as we understand the laws of physics correctly, that's making this impossible. And even if we imagine Eve as actually way ahead of us in terms of technological development, as we imagine these guys might be, as long as we've got the laws of physics correct, then even they cannot intercept a message and not be detected, so that they can quietly sit there and make a copy of the codebook themselves. So this is a pretty big deal, because this is essentially not possible with a classical approach. It's always possible to copy classical information, but the uncopyability, or the fact that you can't mess with one half of a matched pair in the quantum world, is giving us something fundamentally new, an ability to have this kind of communications channel. Would it work in practice? It's been working for years in labs. It's tough to do, but it's not super tough. So you can go ahead and do this and get your Nature paper, and many people have. But there's some exciting developments just in less than the last 2 years. It's actually been achieved now, or relevant demonstrations to this have been achieved by the Chinese, who, at vast expense, I have no idea how much, but it certainly, I would imagine, is in the hundreds of millions, put up a satellite that was capable of shooting light down to Earth in a way that allows exactly this kind of entanglement distribution. So this was, I believe, to 2 mountain peaks. And then very shortly after this result, even more impressively, I guess, they did the same thing on an intercontinental scale. Now, a quantum video call would not be possible with complete... This is just a side remark. It's still very, very early days, and these communication channels only manage to produce a very slow rate of bits that are actually received, especially if it's the space version and not the laboratory version. What you can do, though, is you can do a slightly less secure version of what we've just described. You can allow your zeros and ones to build up for both Alice and Bob, and then you can use that as a key to lock a much larger piece of information like a video recording. That will no longer be invincible to a eavesdropper, because you're now using a small amount of code to lock a big object, but it's still pretty good. So that's what they will have done for that demonstration. So the message is that this can be done not only in the laboratory, but on a massive real-world scale. Not yet, I think, at a rate that will be useful to banks and other entities like that, but this is a huge area of investment, and as you've already guessed from what I said, the Chinese are super keen in investing in that. Okay, so now I must take the last part of my talk and come on to my personal favorite topic, which is computing. So I'm going to risk wasting 2 minutes to just show you what the BBC thinks about computing. Quantum computing, I should say. I don't know if I should, actually, because it's got a rude word in it. Let's assess. Okay, I apologise for the rude word that is going to come in this. Would anyone like to tell me not to put up a video if it's got a rude word in it? Then you're such a spoil sport if you do that. Alright, let's see if it plays. Maybe it won't, and that will put me out of my jeopardy. Okay, so this is a thing. Actually, I think it isn't the BBC, it's one of the other channels, but I don't watch it, but there's a thing called Googlebox, where families are recorded while they watch TV. And then we get to, it's like a reality TV thing, we get to watch their reactions to those various news events and other dramas on TV. So this was done for a story about quantum computing. So
the basic unit of information.
Let me make it go big. Into full screen.
Is either a 0 or a 1. Think of it as a switch which is either on or off. Oh! Okay, no. At the heart of a quantum computer is the qubit. And the magic here is that it can be both 1 and 0 at the same time. The switch can be both on and off.
How can so be on and off at the same time?
How can it be 0 and 1?
Don't know.
Unless it's 1.5.
Well, you don't think there's a number that's on the rock.
Julie love.
It's a nice name, isn't it? Julie love.
Like Julie.
We can begin to solve problems that would take us today more than the lifetime of the universe to solve in seconds, hours, or days.
Piss off. Really?
I think she's talking shit there, to be fair.
So it really interests me that these guys have such a strong opinion about something that they didn't hear about before the previous minute. But so let's have a little bit. Quantum computing is a very big deal. Julie just told us there that things that might take a lifetime of the universe with a conventional computer could be solved on a sensible amount of time, like a day, if we had one. And people didn't believe her, to put it politely. So let's see if I can convince you that such a thing might be possible. So I need to make a quick remark that the thing is that computers are very powerful, but some problems are fundamentally very difficult. So difficult that even our most powerful computers can still not really make much of a dent. And actually a lot of problems in that category, including, for example, simulating chemistry. We'd love to be able to know which chemical reactions will or won't work without trying it in the laboratory, because then we just know what to do without any trial and error. But our most powerful computers can't really do that prediction for us. Here's another example. If you make your eyes go fuzzy, you might see the continental United States emerge here. This is a very famous problem called travelling salesman, where you've got to visit a whole bunch of cities by the shortest possible total route. That is a problem that gets much harder every time you add a city, because it multiplicatively increases the number of possibilities. So if you go from 100 cities to 101 cities, you might say that there's 100 times more possibilities, because now this extra city can be anywhere in the sequence. So some problems are fundamentally very difficult. Those are the ones that we might look to see if quantum computers can help us with. But will they be able to? We've said quantum computers, if they're made out of these qubit things, are weird, but weird things aren't necessarily powerful things. So you have to do some careful thinking there. So the first indication that quantum computers might indeed be more powerful came from this chap, David Deutsch, who we met earlier on when I was introducing the qubit. And he found an example of a problem that I won't talk about because it's a completely artificial, made-up problem that you wouldn't really want to do. But crucially, it was something that a quantum machine, he was able to show on paper, would be able to do better than a conventional computer. And that set everybody thinking. Richard Joser, who's here in Cambridge, was able to boost Deutsch's example to a more compelling and interesting example, but still a very made-up problem. But then came a very famous algorithm that a lot of you probably may have heard of in articles and things. Peter Shaw published his ideas for how a quantum machine could be fast at factoring. What does factoring mean? If I give you the number 4, you know that it's 2 times 2. Those are its factors. Also 1 and 4, but those are trivial factors. So it breaks up into 2 numbers multiplied together. Those are factors. The number 5 doesn't. So if something is not a prime number, then it has factors. But if I give you an enormous number, it's very difficult to figure out what its factors are. And one giant number multiplied by another. That is believed to be one of these tasks that gets much harder every time you add a digit to it. And it is in fact the basis of our codes, many of our code systems that keep our information safe. So it was very much of a big deal to say quantum computers could do this somewhat technical sounding thing fast, because it means that they could break most of the world's codes. That's hugely worrying and also exciting and dramatic and interesting. And it shouldn't really be too surprising that codes, which is something we mathematically as a community have done, as a society have done huge amounts of work on, can be beaten by a new class of computing engine. Here we go from the human brain to the early digital computers. When we go from the current digital computers to quantum computers, again, it's a leap in power that it changes the game changer for code breaking. Okay. So, what else could quantum computers do? Because code breaking always gets mentioned, it's a very interesting example, but it's not very positive. Only a few people in the world really want to break other people's codes. But fortunately, things like accelerating discoveries by saying whether a material or a chemical reaction will or won't happen without having to try it. Optimization problems, traveling salesman was one example, but here we see a port where there's, where are you going? So imagine you're in charge of this port. These little things are the backs of lorries. They're huge, right? So a ship comes in with a bunch of them, and they need to be offloaded, and then some of them need to go onto a new ship. But where are you going to put them all so that you haven't got something that you need under 50 other ones, right? Very difficult optimization problem. And even, potentially, artificial intelligence, maybe another area where conventional computers are just not powerful enough. As powerful as they are, as great as they are, and even though they can beat people at Go, I still haven't got my robot butler, right, who can just have a chat with me and then make me a cup of tea. We don't have general intelligence. In fact, we have much less than that. So AI is still a hard problem, and one where quantum systems might, in fact. So this is in the order of speculation, actually. We know quantum computers would help us with things like chemistry and material science. We're pretty darn confident that they will be able to do optimization problems for us that are important and that would save us lots of energy and time and waste. It's quite likely that they'll help with AI, but that's also sort of an increasing order of how much people care. So these are all hot topics. I've already played that. So, is it a realistic possibility? Can we actually have a quantum computer? Does it make sense? So I give you a quick description of 2 kinds of quantum computer, and then we'll talk more about the one I care about most. All right, so route 1 to a quantum computer has these keywords, if you like. Universal, fault-tolerant, circuit-based. I'm going to say what those things mean. It's the route that most academics study in Oxford and in universities all over the world, including Cambridge, and also in big companies. Most of the effort is on trying to make this kind of quantum computer. Now, many of you may recognize that diagram. It's not a quantum diagram. It's it's very important. It's a logic circuit, essentially, which can translate directly into conventional electronics. Hands up if you've seen some kind of diagram like that one before. It doesn't have to be that actual one. Yeah, so that kind of diagram tells us how our conventional technology works. It shows how the flow of bits coming in from the left and coming out on the right interact with each other to do a calculation. The most natural way to think of a quantum computer is to say, all right, we've got qubits instead of bits. Let's draw the same diagram. Let's give ourselves a family of building blocks like these so-called gates, and gates, not gates, and so on. Let's think of the quantum versions, and now we'll have a language for describing quantum algorithms and calculations. And that's right. That's how it works. You figure out what gates you need, and then you figure out how to do them in the lab. And this is hard, though. It is hard, and I'm going to show you why it's hard in a bit. But this is definitely a comprehensive way to make a quantum computer. There is, however, a sneaky other way of doing a quantum computer, which has made more progress so far because it's not as hard in the laboratory. And this one, I'm just going to bring up all the text and then make a couple of remarks, because this is not the one I'm talking about, but it's fun to give it a mention. It's a radically different view of things, which is very appropriate for solving, say, optimization problems. And you can think of it like this. Nature, if you cool a system... Whoops, I don't want to second off. If you cool a system down, it will lose its energy until eventually it has no extra energy at all. It will be in what we mentioned before, it's the ground state. Now, if you can build a device where the energy the device has reflects the cost of some problem, like the dollar cost of the traveling salesman problem, for example, then just, in inverted commas, just by cooling that system down so that it has the least possible energy, you would have also found the solution to the problem you care about, like how to travel around with the least possible fuel being consumed. And you can take this idea to work together with something very powerful, which you can ask me about if you like, called the quantum adiabatic theorem, and figure out, yes, I can make a quantum machine that I can cool down, essentially, to its ground state, and then I can look at that, and it will tell me the answer to an interesting optimization problem. This requires much less control of the individual qubits, so it's, in a sense, much easier, but also it seems much tougher to apply it to general problems, and we can't even show on paper exactly how powerful it would be. So it's the old scenario that the theorists want one thing. Well, everyone wants it, but the theorists can describe one thing quite comfortably, but the experimentalists really struggle to do that one. And then the theorists can't say much about this one, but the experimentalists can relatively easily build it. So there's two different approaches. And that's very confusing when you Google something like this, because you will find that there's one company that very famously makes these things, and you can buy one. You can have a quantum computer of this second kind tomorrow, probably, if you ring them up and offer them about £15 million. And that's cheap for a machine as exotic as this. It's easy to spend £15 million on conventional computers. But it's a very limited machine, but still very interesting. And we work with these guys looking at that gadget. But I want to spend the last few minutes of my talk telling you about this, the big vision, the direct translation of how conventional computers work into the quantum realm. And I'll show you some sort of good news, bad news about whether we can have that machine and how long it will take. All right? So whizzing on with that. And so why haven't we... So I mentioned this guy, David Deutsch. He's been contributing these ideas in and making us want to have a quantum computer since the mid-80s. And we still haven't got one. But meanwhile, Apple have turned that machine into this machine, which is way more powerful. So there's been exciting progress in conventional computing, but we still haven't got our quantum computer. Why not? Okay, so the problem comes all the way back to the beginning of the talk. It's the problem of controlling imperfection. The thing that was perfect for sensors, and that, although I wasn't asked about it, I can explain that it's not a deal breaker for communications, is very difficult for your computer. All right. So your quantum computer must work with qubits that are in these superpositions, 0 and 1 at the same time. But these superpositions are delicate. If the environment, meaning the surrounding of your computer, in any way disturbs the qubits in a way you don't control, then they are messed up, essentially. It's as if they've been measured without your permission. In a conventional system, we can check if something's gone wrong by looking at it anytime we want. But we're not allowed to look at our qubits because that would definitely mess them up. So how are you going to keep track of the problems that are happening inside your quantum computer if you're not allowed to look at it? It seems like an impossible paradox. But actually, a showstopper, if you like. But this chap, Andrew Steen and Peter Shaw, who I mentioned earlier, came up with a solution to this almost philosophical-sounding paradox. I want to check for errors in my machine and fix them, but I'm not allowed to look at it. How is that possible? The trick is to do a separate little calculation that you do frequently. You pause the main calculation, and you do a calculation that just checks whether there are errors or not. And then you can do that in a fashion that you don't damage the quantum states. So I could again talk a bit more about that, but I just present it to you as obviously a pretty nasty problem, which it turns out there's a beautiful solution to. And this is called quantum error correction. Now, when Andy Steen and Peter Shaw cooked up this theory idea, how did things look? Well, this was back in 1996, and in the lab, we could control things to a sort of plus minus 10% level of accuracy. Meaning when you tell your qubits to do something, 10% of the time they do something else. Now, Andy Steen said, look, I can tell you how to make a quantum computer behave itself using my very clever quantum error correction ideas. But, he didn't say very clever, he was a very modest guy. I bet he was very clever. So, the bad point is that the machine has to behave pretty well. It has to be quite a nicely behaving machine in order for the scheme to be able to then boost it up. And pretty well means something like that, something like 10 to the minus 4, 10 to the minus 5 levels of noise, very low amounts of error. And then you can boost that on and make it into a really well-behaved computer. But that's a gap. How can we get from 10%, which is a pretty rough and ready number, to these very high-precision machines? How long will it take to close that performance gap? Back in the 90s, no one knew, and it was just a question of whether you're an optimist or a pragmatist, maybe, or a pessimist. You could take all of these views, and they were all expressed, and quite credibly. But and so I just had to flash this up. It can be an absolute game-over scenario if errors are not under control. Does anyone know what this is? Fortunately, the resolution is low enough that you can't cheat and read, because it says it right in the middle of it. Anyone who hasn't answered a question care to take a punt at this? And then I'll come to you. Any guesses at all? Say again? Yes, exact answer. It's the analytical engine, which was 100 years before actual digital computers were made to work at the end of the war. Babbage had an idea to make a mechanical one, and it was a correct idea, just like our ideas for quantum computers we believe are correct. But it didn't work. And one could go into why it didn't work, but loosely we can say that a machine of such incredible precision, these are all cogs and this is only a tiny fraction of the machine, could not be made sufficiently perfect to actually turn and process information. And Babbage didn't have a theory to tell him whether it would or not, so he tried and it didn't work. How do we know, will quantum computers go the same way? No, we don't think so, because we're in this situation now. So since we have that big gap, and then we could again take the attitude that the quantum computer might be the same as the Babbage engine, it's never possible to get the errors under control. But the good news, and the reason there's so much money now, I'm just going to finish with that in a moment, coming into the field, is that things look much better now. The theorists have come up with better schemes, which has lowered the bar so that from the right-hand end of our diagram, it's become easier to reach. And the experimentalists have made a heroic effort to put quantum systems in the lab under better and better control. And now we have this situation. In the lab, we can get qubits controlled to better than 1%, and the theorists are saying, well, you can get to 1%, you can have a computer. I can tell you how to then go the rest of the distance and take out errors from your machine as fast as they come in. So that seems like we're done. We can now build a quantum computer. And that's true, but there's a huge caveat. I'm not going to lurk on that slide very long, because it's a very big one. I'm going to give you the bad news. Another word for what I've just described is fault tolerance. It means that as faults happen, we tolerate them, because we can figure them out and get rid of them. It comes at a huge cost. That's the terrible bad news. Every qubit needs to be replaced with a huge number of qubits, which together, collectively, represent information. That's the trick. But that group may be as many as 1,000 qubits just to store the information that really is one qubit's worth of information. So where that leads us is, and so I have this slide, it's very technical, but this is the only relevant number. The number of qubits to actually do a problem that we know is beyond conventional computers, it's actually the code-breaking example again, is 6 million. Is that a bad number? It's a big number compared to what we've got at the moment. We've got tens of qubits in the laboratory at best, and we need 6 million of them if we're going to make a quantum computer that behaves itself. Let's skip through this slide, it's not super interesting, let's leave it here. So that seems very discouraging. It's not, however, so we can work out what it would take. Either a machine that's made out of many components, I'm going to finish in a minute with a video showing you our efforts in Oxford and with partner universities, including Cambridge, all around the UK, to make a machine like that. That's 2 of the modules, it would have many. Or we try and make a device that's a single giant machine, but it needs to have this huge number of qubits if it's going to be able to remove errors. Get over the problem of errors. And here are some other devices that people are working on around the world. IBM and Intel and also Google are all furiously going in their own ways at trying to make a machine that can have many qubits inside it. This is a race, and 4 years ago the government put 270 million into the UK to try and speed us up in that race. And this year we've got some more money, which is £20 million for computing. Some of the rest of the money goes in the other things like sensors and communication systems. And then that's not very generous, right? I could probably. There's a missing M. So 35 million as well for, and this was mentioned in the budget, and it's not quite clear to anyone exactly what it means yet, but another bunch of money for a quantum computing sensor. So the investment continues aggressively. And I'm going to show you the UK effort is centered around Oxford as the lead of an entity called NQIT. You can go to that's NQIT. You can go to nqit.org to read more. And all these universities, you can see Cambridge is in there, are working together with all these companies to try and make one kind of quantum computer work. I'm going to show you that video in a sec. In fact, maybe I'm going to show it to you now. Right, so let me show you the way that, it's not the only way, the UK is actually exploring a bunch of different approaches. But this is the one that's got the furthest. And it's got a narration, this video, but it's just my voice, so I think I may as well just narrate it to you live. Since, okay, so if we now, let's turn that off, and just get it to go full screen. So this is now looking inside a quantum computer. We'll wait a second and that will go away, I hope. Yep. And it's showing us a couple of atoms. This is a calcium atom and a strontium atom. Artist's impression, of course, because you can't really see atoms with normal light in this way. Now, each one of these guys makes a great qubit. We can set its state, here we're using colours, between 0 and 1, and it will stay that way for a nice long time, and we can read it out using a laser. If the thing is in state 0, a laser will do nothing. If it's in 1, a laser will make light shoot out of it, a particle of light called a photon. So just like the NV center, really, this is a very nice building block qubit. Now here we see a bunch of them, and they seem to be floating above a gold layer, because they are, in fact, floating above a gold layer. So this is a series of little electrodes that are attracting and repelling them very fast, so that overall they just stay locked in place, and that's how we hold them in place. Now we're zooming out. This chip is the size of your thumb. We're zooming out a bit more. This is sort of laboratory gubbins that can one day be miniaturized. But crucially, this is a vacuum chamber. So what we don't want is air molecules going and knocking around our lovely qubits that we're working so hard to control. So we put it all inside a vacuum. And crucially, we also have a gadget here which collects the light. You saw light comes out of qubits under certain circumstances. This catches that light. Now, this overall entity is a little quantum computer. However many atoms we've trapped in the middle, that's how many qubits we've got. But if we had 2 of these devices, we can create quantum entanglement between the 2 of them just by measuring the light that comes out of them. It's a very beautiful way to make these 2 separate gadgets that you could walk between, 2 halves of the same machine. And then, given enough resources, you can just have more modules. And that's how you can make your computer as big as you need it to be, and still the complexity of it in terms of the engineering challenge stays the same, because you're making it out of fixed modules. Now this is, I think that's the end of that video. So the idea there is to make a machine, it won't be small, but to make a machine that can scale to whatever size you need it to be by adding on more modules. You could get to hundreds of qubits and explore whether or not a machine with hundreds of qubits is useful. I won't go into that now, but I'll answer a question on it if you want, because I want to get to the end so people can leave if they'd like to. I think we have good reason to think that even though the things we've thoroughly worked out on paper need at least 1 million qubits because of this whole problem of errors and controlling errors, but as few as 50 qubits might be useful for calculations. We have good reason to think that they might, or certainly into the hundreds, but we can no longer rigorously show that they would because we can't control the errors in that scenario. So we hope that as this kind of machine comes online, first, it will be a machine that might be useful, and as we add more and more modules, it will come towards the scale when we know it can be useful and can do these amazing things that conventional computers cannot do for us. And that is where we are. Now, I could tell you more about the progress. It's basically extremely encouraging. Before we started this project 4 years ago, and I say we, I'm not an experimentalist. They don't let me in the lab because my elbows are liable to put them back several months by knocking over something. But those guys who, in Oxford and with their collaborators around the country, needed to do a bunch of things. They needed to show very high quality operations between the qubits. They've done that. They have the world record for it. They needed to be able to show that they can do operations between two different kinds of atoms, for a reason I could go into. They did that. They were the joint first in the world to achieve that. And crucially then, the thing that you've seen in the video is that they need to be able to take a system there and a system there and create quantum entanglement between the two of them to unlock this scaling. Now, it's not my job to tell you how well they're doing with that, but I'm smiling. Okay, so that is something that you may like to keep your eye out to see what their progress is with that. So essentially, the key science that allows us to build a scalable quantum computer is done. And the decision is, do you go nuts and try and build one with thousands or millions of qubits, or do you build one with a smaller number and then think, oh, wait a minute, I could have made that machine much more cheaply. I could have made that module not for hundreds of thousands of pounds, but thousands of pounds, and then start again. And that's probably the sensible thing to do. It's the difference between what I call the Manhattan Project, which was what made the nuclear bomb approach, where you just put a massive amount of money and just go for it immediately, and a more sort of developmental cycle, and I think that's what we should really do. But this path, and some others, look extremely promising for actually being able to get well-controlled, freely scalable computers. So I think I'm over time, so I'm going to leave it there. But if there are questions, I have lots more slides, and I can. But I'll try and answer the questions quickly anyway. All right, thanks a lot.